Valence bond theory. The goals of this podcast will be to review the difference between valence bond theory and molecular orbital theory. Then, we'll learn to recognize and identify the shape of sigma bonds, pi bonds, and multiple pi bonds. A quick review on our two models of bonding and the difference between them. In MO diagrams, we mixed atomic orbitals from different atoms to make new molecular orbitals. These molecular orbitals form the bonds. Valence bond theory, on the other hand, models bonds as being formed from overlapping atomic orbitals. So, the orbital belongs to the atoms, but by overlapping them, they are able to share electrons to complete octets and form stable electronic configurations. Let's also remind ourselves of how this bond overlap relates to bond length. Taking the simplest example of H2, the s orbitals of H must overlap by coming close to each other. If they are too far away, represented here, there's no bond. But if they are too close, such as over here, then the nuclei, which are positively charged, will start to repel. But there is an ideal distance where the electrons are able to be shared, but the nuclei do not repel, and this creates the bond. This is represented by this potential well here. We have two types of bonds with names based on their symmetry. A sigma symmetry has symmetry that goes along the bond axis, such as from here to here. Or for the CH bond, from here to here. These are freely rotatable if there are no pi bonds present. So the CH bonds here are freely rotatable. Here, freely rotatable. Here, freely rotatable. Pi bonds are named due to their symmetry, which includes a plane that goes along the nodal axis. So this is the nodal axis. This is symmetric over that. This is the nodal axis. This is symmetric over that. Because p orbitals have two lobes, and those must overlap, this locks the rotation, so that double and triple bonds are not rotatable. Now let's look at how these are formed a bit more closely. Sigma bonds are formed by many different types of overlaps. These bonds are bonds that connect all the atoms. The single bonds are sigma bonds, and one bond of the bonds in a double or a triple bond is a sigma bond. Here I'm showing the simplest version of a sigma bond with two overlapping s orbitals. But sigma bonds can also form from the overlap of an s orbital with a p orbital or a hybrid orbital, both of which will look similar to this one. They can also be formed from an end-on-end overlap of the p orbital or a hybrid orbital. Notice what I said here, end-on-end overlap. This is what gives the sigma symmetry. So, lots and lots of options for sigma bonds. S orbitals, p orbitals, hybrid orbitals can all form sigma bonds. Your hybridization is generally chosen specifically to give you the number of sigma bonds and lone pairs needed. So largely, if you have a hybrid orbital, those will be forming your sigma bonds. However, lots of times you won't have any hybridization, and this is where s and p orbitals can also form these sigma bonds. Now let's look at pi bonds. These are formed with two p orbitals, one from each atom, and when they overlap on a side-on-side arrangement like you see here. So this purple lobe and this purple lobe are one pi bond formed by the p orbitals here and the p orbitals here. This is another set of pi bonds. The purple is one pi bond, the green is one pi bond, formed by the overlap of the p orbital here and here and here. Now let's look at another example. So a reminder. Our sigma bonds are cylindrically symmetrical along the bond. So here we would have a bond to bond, bond to bond, bond to bond. They are cylindrically symmetrical along that bond. These are freely rotatable unless a pi bond locks it. So pi bonds are symmetric across an internuclear axis, across that plane. They have two lobes that are symmetric across that plane. And these two lobes lock the rotation so that no rotation is allowed. Here is an example with CH3, CHO. Look at the pink orbitals here. You can see how these side-on-side overlaps of this carbon's and this carbon's p orbitals will form this double bond. This forms the double load structure. So this is one of the bonds. This is another bond. The pink is one bond. You can see the sigma bonds are being formed here and here, here, and the yellow back here, between this carbon and this carbon, and between this carbon and this hydrogen. And the pi bond is represented by the pink. And again, the pink is just one pi bond shown here, which is represented right here on the Lewis structure. Triple bonds, much like double bonds, are formed from both sigma and pi orbitals. There's only the possibility for one bond per bonded pair to be a sigma bond. So with a triple bond, as we have here, the other two must be pi bonds. So here for carbon and carbon, hydrogen and hydrogen, there are now two p orbitals that are forming two pi bonds. And so the purple is one pi bond and the green is another pi bond. These lobes lack the rotation of the triple bonds. So now you should be able to remember the difference between valence bond theory and molecular orbital theory, and hopefully recognize and identify the shape of the sigma bond, pi bond, and multiple pi bonds. What we haven't covered here, but we'll do in future videos, is to more carefully identify which orbitals are making up each bond in a molecule. But you'll need to learn a bit about hybridization to be able to do that.